So I'm just going to make up a problem here. Oh, wow. Okay. Okay. Let's see. What is the pin thickness? What thickness is that? Okay. So say you had a water tower and you wanted to come down here and you wanted water to come out the other end to supply like something like I don't know, something to like you feed your cattle or something. So it drops in here. The rest part doesn't matter. You just want to know the flow rate. So let's say you ended up with something crazy like 1,000 feet. So maybe your water supply is up a hill, at the top of a hill, and then say the length of the pipe is 2,000 feet. And let's say you just have 4-inch diameter pipe. So we're going to monkey around to figure out, so the length of the pipe is this. We'll say E over D is maybe 0.001. I always know that 0.01, 0.1001, those are all individual lines on the Moody diagram. If you look up here, I'll tell you what I'll do. Let me just copy it. I'm going to copy it and move it back down here. So we'll just put it, say, right over here. It may be huge, but I'm going to shrink it. So the actual question that the guy wants to know is what's Q? How many cubic feet per second of water is going to flow out of there? Now, he'll probably want to put a valve here, but let's say the valve is completely open. So the thing is open completely. So how do we do that? What we do is we write Bernoulli's equation between the top of the water, which is exposed to the air, and the exit. So P1 over gamma plus Z1 plus rho, or say V1 squared over 2G, minus the F L over D and V squared over 2G. This will be the loss in the pipe that we'll have to come up here to find. And that's going to be P2 over gamma plus Z2 plus V2 squared over 2G. Now, if you make that little chart, location 1 and location 2, P, Z, and V, then what do I know? I know the pressure at the top is 0. I'm going to take my datum as being right here. So I know the physical, diesel you'll almost always know. So my physical location for 2 is going to be 0. For location 1, it's going to be 1,000. I know the reservoir is fairly large compared to the diameter of the pipe, so I've got that. So now I know I can write between here and here. The extra thing I know is the water is squirting out straight into the atmosphere. So I have everything figured up except V2, which is what the farmer or the whatever, the cattleman wants to know. So if I go through here, I'll see this. I'll see 1,000. I'll see this. I'll deal with this. This is the part I'm going to have to deal with later. P2, I'll see 0. I'll see 0, and I have that. So what I've got is 1,000 minus F L over D v squared over 2g is equal to v squared over 2g, where v is the whole, in the whole pipe, it's the velocity. Since the diameter is not going to change along the pipe here, then these velocities are going to be the same. Now, what we did is we decided, or he noticed that the length of the pipe is 1,000 feet. The diameter of the pipe is 4 inches. So that has to be converted there. And actually, let me rewrite this before I put the numbers in. Because I think what I want to do is I want to move this to the other side. And so 1,000 is equal to. And so what I'm going to do is write 1 minus F L over D, put that in brackets, and that actually should be plus, sorry, V squared over 2G. Now I'm going to put stuff in. So this moving over, this V squared and this are the same thing. So this should make it reasonable. If I wanted to, I could actually just do this, call it H. And then what I'm going to do is, before I put in numbers, I'm going to work this out. V is equal to the square root, take the 2g and move it against that, is 2gh over 1 plus f L over d. I made my square root go too far. So the first thing to notice, is if f was equal to 0, v, okay, wait, let me say all this first. If f is equal to 0, there were no losses. And therefore, if that was the case, then this would be the case, 2gh, what we would notice before. So you would get a number. So what we'll do is we'll solve that number, then we'll solve the other number, because this will give us a reference. If f is not equal to 0, then v, okay, think about it. Okay, let's think about this for a minute. I had to move that to the other side. So you would have a number in the denominator that would be added together. So, okay, so it's hard to say relative magnitude of this to the number 1 because it depends on the problem. But the denominator would go up. Okay, so if this number went up above 1, say it went to 4, just as a case in point. I don't know what it's going to be. So let's say it went to, or let's say it went to 3, because then 1 plus 3 would be 4. And so then, if that were the case, then what you would get is 2gh over 4, meaning suddenly this 4 could be pulled out, 2gh, and it'd be over 2. So what would happen is the velocity is going to be lower here than it was up there. And so as you increase f, or the length of the pipe, or decrease the diameter, f is, that whole term on the bottom is going to climb. And you're going to get a lower velocity. How much lower? I don't know. Let's find out. So, oh gosh. So let's put in our numbers. Okay, first let's fill them out. H was equal. No, I got a Claritin in there. I might take in a minute. Because if I do a cough drop, I'd be coughing it onto my screen. Oh, this flu I had 3 weeks ago This cough has not left. Okay, so H is that. G is 32. That's funny. 32.2. L was, what did I say, 2,000 pi? Yeah, 2,000. It's 2,000. This has to be larger than that. Otherwise, it's not possible. That would be physically impossible. So we made it 2,000. And D was 4/12. F is not available right now, but Moody will make it available. We'll deal with that in a minute. But let me stick all these in there and come up with V equals square root of 2, 32.2, and then 1,000. That's how high the tank is up there. 1 plus F, which I don't know, 2,000 over 4/12. Now that I have that down, I can sort of scroll down, sort of figure that out. This time, I got that F stuck in there. So I really... 1,000 times 32.2 times 2. Well, hey, you know what? I'm going to do something. Well, I'll just do this. Over 2,000 over 1 plus 6,000 times F. Just out of curiosity, what would happen if I took the square root? Oh, it's not. I thought it might come out to be a integer up there, but it's not. So I got that. So I got that. And then I have this. I'm just going to drag it down here. Put it right next to it. Now, if you look at this, this is one of those, hey, how do you do this kind of thing? The Reynolds number is equal to velocity, diameter, or row velocity diameter over mu, which is the same thing as what he has. It's just, I usually don't do that because I can't write this symbol very well. But that's the viscosity, that is the dynamic. That's why I like to write it this way. So these are both the same thing. We'll assume this is water. So if that's the case, 1.94 slugs per cubic foot. And mu is equal to 2.34. And we saw the other day how this varied quite a bit, e to the minus 5. So we got all those. You know what? And we have diameter, 4/12. But what we don't have is the velocity, because that's what we're looking for. So the question is, how do we do this? And so this is this concept, iteration, So here's the way I start these problems. I first find out the E over D, which I wrote down here somewhere, 0.001. So if I find 0.001, that's this line right here. So now something interesting about the Moody diagram. And what is interesting is if you look everywhere back on this dotted line that says fully turbulent flow, you'll find something interesting. Almost all of them are flat. They're almost all flat. So this means for our pipe, if the Reynolds number was above that value, it would not be an iterative problem. So say the first time I solved it, it was that. Then I went through and did it again. Next time it was that. And then the next time I did it again, it's that. So the difference between these two is almost indistinguishable. So the way I look at this is I go in and I say, okay, if that's the case, I can just go in here. Okay, so we don't care where it is. We just know this. And we'll just take a red marker and we'll go all the way across to here. This is the value if it's completely turbulent. So let's see, 0.15, 6, 7, 8, 9, and 10. So let's see, 16, 17, 18, 19.0195. How about we just guess this? We're going to guess this value. Now, what do we have and where can we go here? If we have this value, f is equal to 0.0195, I can stick it in here and I can get back my v. So let's try to see. This is where something like MATLAB might come in handy. Let it come up here. So I'm just going to guess f is equal to 0.0195. And then I'm going to go in and put in this equation. V is equal to the square root of 64,400 divided by 1 plus 6,000 times f. So I'd get 23.362. So 0.0195, it's 23.62. Now, I can go in and solve the Reynolds number based upon this guess. Rho, velocity, diameter over mu, which would be 1.94. Let me make the pen a little thicker. First, I guess I'm that one. Because I'm going to try to use the thing here. 1.94. Well, no, I'll do the other way. 23.62. Or I'm just going to put in V, which will be that for the minute. And then diameter, which will be 4/12 over 2.34 e to the minus 5. I'll see if it'll let me go to MATLAB, and it won't let me unless I do that. So with that, okay, Reynolds number is equal to 1.94 times the velocity times 4 divided by 12 divided by 2.34 e to the minus 5. 642,000. So it turns out 642,000. I just throw some of these digits away because one of the things I'm not able to do, I'm not able to tell the difference that much. So about 640,000 looks like about that way to me. So now, if I can get my ruler up there, how do I get my ruler? I guess I got to go back, just full screen, move my ruler up, then come back to not full screen. Go to 90 degrees. And now I got to get it so that I'm there. Now I'm this blue line, so I've moved to this point. Because there's my blue line. I've moved up to now where there's where they cross. And then I can move to about right here. And my second run in there, I can pretty much say, okay, okay, 2, 4, 6, 8, 10. So 21, 22, 23, 24, 25. So 2, 3, 1, 2, 3, 4. How about 3, 8? I mean, I don't know that this is that accurate. 2.384. I mean, 0, 2, 3, 8. Okay. Gosh. So the Moody tells me that F as a function of the Reynolds number, and E over D becomes 0.0238. And I'll even do the little squiggly kind of equal to. So now I take this and stick it back in here. And velocity at F is equal to 0.0238 equal to. Now here's where that MATLAB comes into good play, because I can say F is equal to 0.0238. And I can hit the arrow up a couple times and get my new velocity, 21.162. Then I can hit my arrow up with that so I can find my Reynolds number. My Reynolds number now is equal to 582, and I'm not even going to worry about those digits. Now, a 582, okay, 582 is probably somewhere maybe right there. So if I go out now, get my ruler, shrink the whole thing down, maybe use a different color so it's a thinner pen. Okay, oh, there we go. And what's funny, now I come to 0, zoom in on this little monkey, and what you find out is I moved from this location up to about right here. And my contention is I think you're not going to find that much different there. Technically, it's almost like the thickness of that line, if you think about it. It's only a tiny amount more, so maybe it's 0.02. Let's just say it's 0.024, which would be right there. And then if you go back, I'm going to get rid of this. So if you go back and you say, okay, F, the friction factor, as a function of the Reynolds number, and E over D is equal to 0.024. Then you go back, what you find out, okay, so let's go back, 0.024. Velocity is 21. So velocity at the friction factor equal 0.024 is going to equal to 21.075. And the Reynolds number is going to be, okay, oh shoot, I hit that too many times. That, then this. No, this, then that. Okay. Arrow up, and again, and what you find out is 579, or almost 580, which isn't that distinguishable from there. And so at this point, I would say that velocity is going to be pretty much it. So I'm going to guess that I'm going to stop the iteration there and say, okay, V is equal to 21 feet per second flying out of that pipe. What would happen if there are no losses? If there are no losses, V is equal to, let me go back to the other pen. No losses, V would equal to the square root of 2GH, which would equal to 64,000 because the F wouldn't be there. This wouldn't be there if there were no friction factor. Yeah, and it'd all be over 1. So it'd be 64. 4? Yeah, 4. Which is, I think I calculated that a minute ago, and I think I deleted it. 64, 4, and then take the square root. 253 feet per second. So there's a big difference here if you don't have losses and if you do. This is reasonable, and this is completely unreasonable. I mean, that's just not even on the charts. So you can see, if you don't include losses and you have a lot of, like we went through 2,000 feet of pipe and we went down 1,000 feet. That's a lot of distance. There's plenty of ample time as a particle goes through there to lose energy due to friction. So the fact of the matter is that this thing lost a ton of energy as it went down there. So the difference of 253 to 21 is big. So that's the way you do it with the Moody diagram. You're just sometimes you've got to iterate. The convenient thing, it's not convenient by design, it's just convenient factual. And that is that as you go out these things, they remain constant, almost constant throughout this whole region. So if that's the case, I'm going to use an educated guess, and I'm going to basically guess using the flat line here for whatever E over D. No, I was down here. I'm using that. If I had 0.01, I'd use this one. And then that would give me my first F. And then I'd go find the V, and then I'd use the Moody diagram from there. So the next thing to do is kind of to try to identify what was what here. Okay, this equation was generated from Bernoulli. This will always be the case. This equation is just a kind of a factual equation, definition. How about that? And then this is the Moody diagram. It's really an equation. So this is Moody. How about we say Moody equation? And I'll go ahead and be a little bit more respectful, make it capital. And those are the three things you got. That's it. Well, I guess you've got the E over D in there that somebody's going to give you. So you got to come up with the E over D in addition to the Reynolds number that comes out of there. So my sequence would be, I don't have F, I don't have V, I don't have Reynolds number. So I'll make an educated guess of what friction factor is, solve for the velocity, carry that into the definition, carry that to the Moody diagram, then turn around and go back here and just keep looping until, something that you're comfortable with doesn't change that much. And if you think about it, even our first shot wasn't that bad compared to the second shot. So, even if you're in the field and you just run one time through there, it's better than, not assuming there's no losses at all, because the difference between 23 and 250 something, that's huge. So even if you went with that, that's much more accurate than having assumed no losses. So there's one other topic, and yeah, we got time, we can cover that. And that is, if you put a valve in there or something, it doesn't have to be a valve, it can be anything. Kink in the pipe, let's say the pipe came through. Okay, it did something weird here. let's say the pipe came through, it did some sort of weird thing like that. So here's your water coming through here. For some reason, there was a kink in it or something. There's going to be some losses here. So there's two ways to do that. And these are often termed, or they're always called, minor losses. But that has nothing to do with the size of it. Sometimes these are larger than the pipe losses. So there's two types of losses. There's pipe losses, loss in the, as you go down a whole length of pipe, and that follows the equation F L over D V squared over 2G. Then you have the thing called minor, and those could be a valve. They could be anything. So what it is there is it's just anything but the pipe. So if there's a valve, there'll be some losses there. So there's a weird elbow in which the pipe is, there's going to be losses by having to turn that corner. What they do is they see KL V squared over 2G, where this is a factor. Now, I guess what we'll do is we'll look at the book next time. However, there's something interesting that people do in the real world. And if you stare at this equation and then stare at that one, it makes perfect sense. And what they'll do is they'll say, somebody will deliver like a valve to you. Okay, here's my valve. It's, whatever. It's, they have the whole definition of the thing. Here's my valve. I'm going to give it to you. They'll say the length equivalent is 3 feet. And so what that means is, okay, if you compare these two, KL V squared over 2G compared to FL over D V squared over 2G, that means that this is equivalent to a 3-foot length of pipe. And that's all it is. So let's say you had 3 of these. Let's say you had a pipe that's 1,000 foot long, or maybe make it 100 foot long with 3 valves in it. Then it'd be 3, 6, 9. So it would be effectively 109 foot length. And you would just put that in there. Right. That's right. It would just act like it's 100. So most, I would say from what, I used to work in the field a little bit, and I would say I didn't look at everything, but what I did look at, I realized about 80% of the time, they're giving you the equivalent length. They don't give you the KL. So when you go out and get a manufacturer's thing, they're giving you this more often than they're giving you that. But in the textbook, they more often do that. In the real working world, they do that. And that's they're one and the same. They're exactly the same. Yeah. There's only one slight difference. If you really think about it, the slight difference is this is going to be constant no matter what. The friction factor actually is a function of the Reynolds number and the E over D. So as you change this Reynolds number down or up, you're going to change this. But you never change that. And to me, that makes more sense. So it makes more sense that you would supply this as an equivalent length, because if you're pushing very slow flow through there, you're not going to have as much turbulence. And if you push high, you're going to have more turbulence. So the fact of the matter, the friction factor inside this, the K, what I'm saying is the KL is probably going to be a function of the Reynolds number anyway. So if it's a function of the Reynolds number anyway, just make it delivered to the customer the equivalent length. Now, valve is funny. It's the funniest one there because they'll say percent open. Okay, so if it's 0% open, what do you think the friction factor would be. Or let's say this, let's say KL. If you have the thing closed, there's going to be no flow through there. So you're going to have something that kind of goes like this. So that, that loss coefficient when it's closed, KL, probably going to be infinite. So then you start opening your valve, it starts dropping, you're allowing more flow to go through there. So there's going to be a plot delivered to you that is either going to be, it's going to look kind of like this. It's either going to be L equivalent, or it's going to be KL over here in percent open. When you're 100% open, this is, in certain valves, you've seen those valves where they're like a sphere with the hole drilled right through them. And you turn and you line them up. They look straight down that pipe. You're going to find that this is going to be fairly low on those type pipes. If you've got that valve where it has a seat and it comes off and it's fully open, those valves, what happens is the water comes in, the little seat is up here. It's maybe like a, oh gosh. Yeah, like a plunger looking thing. I'm trying to, this doesn't look good. Sometimes it even has a little rubber right here. And then it goes through here and it has this thing on it. Usually there's a piece right there and there's a hole right here. When it goes down and sets right now, this thing will open, it can come around this. But if it goes down and sits on it, it just closes it right off. It's, you know what, I could find the book, but actually it might be better just to go, there's just as much information online. Plus we got to go in a minute anyway. Let's see if I can see what valve types. There's got to be something. Okay, yeah, there's those kind of too. The butterfly valves, I forgot about those. There's all sorts of different valve types. Types of valves. Okay, let's see. Well, that's just an image, but often you can visit. Okay, you can visit the place. Okay, so you said, oh gosh, look at all these butterfly valves, all those. I'm looking for actual, oh, here we go. That's the one I'm talking about. It's funny looking. It's kind of weird. You come off the seat, but that's really weird because the flow comes through there and it's swirling around to come down this thing. There's still going to be a lot of losses, even if that's completely open. So, yeah, it could be thought of as that way. Then you got this one, which actually in the open position, it'll be a little turbulence at the top and at the bottom, but not that bad. And then there's, oh, I thought they were going to show me, there's a butterfly valve. Where's the butterfly valve? Is like a circle. Yeah, and it just, yeah, it just, right. Yeah. Now this, I don't see, I haven't seen this as much. The diaphragm kind of pushes and pulls that little slip. Still, you're going to get losses turning there. Reducing valves, pinch valve. Well, there was the other one too, but I don't see it. Needle check valve. You see it a lot in, let's see if I can find it in here. Yeah, no. Butterfly check valve. You know, the one I'm talking about really doesn't work for really high pressure anyway. Okay, so that's about it. Anyway, each of these valves, when they're open and closed, they'll each have their own, point when they're completely open. Some types of valves will have a little bit less loss when they're open. Some will have more. So you can just get all that from the manufacturer. So you don't have to generate those. So I guess we should go downstairs and do the, so I don't have to use this down there. He gave me a set of slides. I don't know. We'll